Okay, we're going to continue on here. Chapter 15, we talked about solutions there. Uh, we were talking about really concentrations last time. So we talked about some concentration units. We got our percent concentrations, our percent mass to mass, which again is our mass of our solute divided by the mass of the solution. As we talked about, right, it is the bottom part here is really important, especially in these type of problems, as they kind of give you both the solute and the solvent separate in these type of problems a lot of times. So you want to make sure that you do add those together to get the true mass of the solution. We also have percent volume to volume, which is the volume of the solute, the volume by the volume of solution times 100%. And we also had percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. And all these sort of percent concentrations, one easy way to sort of use them in a calculation, besides obviously you could just plug and chug into these formulas here, is you could take a more dimensional analysis approach, especially if you're given something like the percentage. You could just assume 100. So again, if you have like a 2.5% by mass there, sodium chloride solution, that would mean you have 2.5 grams of sodium chloride in 100 grams of solution. And again, you can use it as a conversion factor, or you can flip it around. 100 grams of solution is 2.5 grams of sodium chloride. So sometimes that's an easier approach, especially if you're given sort of the percentages, just to kind of turn them into a conversion factor and use them in a dimensional analysis approach. We then talked about really the big unit of concentration, which is molarity, which is moles per liter. It is technically moles of solute per liter of solution. You should think of this as a formula and be able to solve for any of those things, which we very commonly do. So if you want liters, that's going to be your moles divided by molarity. And if you want moles, which is a very common sort of calculation that we do, we take liters times molarity. We also talked about the idea that if you did have a molar solution, say, of sodium chloride, and you want to use this in a calculation, it's a really good idea to get rid of the big M and treat it more like again, a conversion factor, so you can see both of those units. So again, that would be 2.5 moles per liter. The number always stays with the moles part. It's always 1 liter. And again, you can see at least both of the units that are there. As I mentioned last time, very common mistake. People just see the M and think moles only. They don't think about the liters part of it or the volume part of it. So it's really important to see both of those units. That's why, as well, it's really important when you do this calculation that your volume is in liters, because technically when you use your molarity, you're using moles per liter, so that the liters properly cancel out and you're left with moles, which is probably what you're looking to calculate in that particular calculation that you're doing. We also talked about that if you actually multiply milliliters times molarity, what you're really doing is taking milliliters times millimoles over milliliters, and those cancel and you actually get millimoles. So there is a 1,000-fold difference, right, between those two. So if you're using molarity by itself and you have volume, always convert it to liters, because probably 99.99% of the time, the unit that you're really looking for is moles and not millimoles. So you won't be off by that factor again of 1,000. So it's really important to keep that in mind as you do it. When we talk about concentration, we could also relate concentration to ions that we talked about. So sometimes in a solution, pretty much in every solution, if you have ions, they are the guys that are floating around basically in the solution. So sometimes we're interested in maybe just the concentration of a particular ion that's floating around in the solution, but we know the concentration of the ionic compound together. We can use sort of like a stoichiometry relationship to figure out the concentration of the ions that are present. So if we had a 2.5 molar solution of barium chloride. Again, when we look at something like barium chloride, it would break apart in solution as a barium ion and 2 chloride ions floating around. So how concentration works is really kind of like stoichiometry. It's a 1-to-1 relationship between the whole thing and the barium chloride. So I'll put this down here. So this is 2.5 molar. So we would take 1 times the concentration here, and it basically will be the same. So in a solution of 2.5 molar barium chloride, the concentration of the barium ions that are floating around would also be 2.5 molar. But when we look at the whole thing to our chloride, it is a 1-to-2 relationship. So in terms of the concentration, we do need to multiply it by 2. And I'll do it without the calculator and hope for the best there. That is 5 molar, I think. And that would be the concentration of the chloride ions floating around. So just visually, if you think about one of these guys going into solution, you basically have 1 barium and 2 chlorides. You have twice the amount, right, of chlorides as you do barium. So it's twice as concentrated. And again, that's sort of what the concentration there reflects. So sometimes it's very common when you're dealing with molarity, and especially ionic compounds, that you may be interested, again, in not the whole thing, but just the actual individual ion by itself. And again, that's how you could relate it. If it broke apart into like a 1-to-3 relationship, you basically can multiply the concentration by 3 to get the adjusted concentration. We finished up, I think, talking about dilution last time, and dilution is really when we add more solvent. And in a lot of cases, the solvent that we use a lot is water. But again, not always, but technically you're adding more solvent. So what happens in a dilution is we actually lower the concentrations because, again, molarity is technically moles of solute over liters of solution. And once again, our solution is both the solute plus the solvent. So when we do a dilution, as I mentioned last time, really the only thing we're adding is more solvent. And that's actually going to increase the volume of solution, which means the bottom part here will get larger. And that means that our molarity will actually go down as a result of that. And that's basically what happens in a dilution. The one thing that does not change when you do a dilution is the solute. So the solute basically stays the same. So the moles before the dilution will equal the moles of solute after. So kind of before and after the dilution, the moles of those solutes will basically remain the same. There is a dilution equation that we commonly use, which is M1V1 equals M2V2. We also talked about there's kind of a more generic version of this, which is C1V1 equals C2V2, C just meaning concentration. You technically use any type of concentration you want in this formula. I will say molarity is probably the most common, which is why a lot of people roll with sort of this equation here. This is also the equation that we talked about as well last time, that this is the one place where if you do want to leave your volume in milliliters, it will be okay, as long as it's milliliters on both sides, because they will cancel out correctly. Or if you have 2 molarities in 1 milliliter in terms of volume, that will also be okay, because the molarities will cancel out and your answer will be in milliliters. So this is the one place where you can leave your volume in milliliters if you like, if you're specifically using this equation. If you want to convert it to liters as well, you could do that as well. But definitely, as we talked about, when you're using molarity and volume by itself, not in a dilution situation, you should always convert it to liters. That's pretty much what you're going to want to do. The M1 and V1 is usually before the dilution, and the M2V2 is usually after the dilution. Usually these guys are the more concentrated guys, and these guys are the more dilute solution. Any questions on that there? All right, so I think we did an example last time, so I think we're on this example, I think. So why don't you do that? What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium? Okay, so let's take a look. So this is situation. We basically got a bottle sitting here of some calcium nitrate. That is 5 molar. And we want to make a new sort of container that has a volume here of 500 milliliters and a molarity of 0.25 molar. And obviously our original bottle here is 5 molar in terms of it. So this is a dilution. We could do our M1 V1 equals M2 V2. In this case, this would be M1. Obviously, these would be 2s. And obviously, we do not have V1. So we'd be solving for V1. So we're going to send that to the other side. That would give us V1 is equal to M2 V2 divided by M1. Putting in our numbers here, again, we'll go with 0.25 molar. I do not necessarily need to because I'm using this equation here to convert it to liters. I can leave it in milliliters. Again, if you want to convert it to liters, you can. We will leave it in milliliters here. We'll divide by 5 molar. Once again, this is why we don't have to convert it. The only difference is my answer will be in milliliters. If you convert it to liters, your answer will be in liters, obviously, if you did that. If we do that there, that looks like a 0.25 times 500 divided by 5, going to give us 25 milliliters in this case. Question on that. That, by the way, is not the answer, though, right? We want to know how much water that we need to actually add, which, as I mentioned last time, is a very common sort of question. What we just figured out here is V1, which is how much of that calcium nitrate, more concentrated solution, we need to take. So what we just figured out is that we need to take 25 milliliters of that guy from our more concentrated one. Remember to find the amount of water that we need. Typically speaking, the volume of water in this case would be our final volume, really, minus what we just put in there. So we want to end up at 500 milliliters. We just put in there 25 milliliters. That means we need about 475 milliliters of water to go in there with it. 475 milliliters. That's going to give us a grand total of 500 milliliters. And if you do that and you give it a little mixy, shaky, maybe not so much shaky, and you mix it together, you will then have a solution that has a molarity of 0.25, and you will have 500 milliliters of it at that point. Any questions on that there? So very common type of question for dilution is, like I said last time, like how would you make the solution? How much water did you need? So you want to be really careful when you come across a dilution equation that you are actually answering sort of what it's asking you to answer. Any questions on dilution here? All right, then let us continue on to the next wonderful topic of stoichiometry, because we've done stoichiometry in a lot of different ways. So why not do it with solutions? So just like we've done regular stoichiometry problems, just like we did stoichiometry problems involving gases, super common stoichiometry problems involving solutions. So the good news is no matter what type of stoichiometry problem it is, regular, gas one, solution one, most of the steps are pretty much the same. The main difference is a lot of times, as we saw, say with the gas one, maybe how you get your moles or what you do with it at the end. And that's the same thing that applies here. We still really use our same steps. So we still want to make sure we have a balanced equation like any normal sort of stoichiometry problem. We also want to make sure that we convert to moles. We also want to make sure, right, that it is a limiting reagent problem or not a limiting reagent problem, I guess is the other way as well to think about. We want to then do our mole to mole relationship. And last, we want to convert our moles to some other unit. So very much like sort of what we talked about with gas stoichiometry, I would say the two places that are different typically in a lot of solution stoichiometry problems is here, the second step. So I will say you will still in a lot of problems still perhaps do the grams to moles, which we use our molar mass to do. But very, very commonly in solution stoichiometry, we have molarity given to us, and we oftentimes have volume given to us. So it is a very common place here for sure to use molarity, which is our moles per liter. And the way that we would use it in this case is to solve for moles, which would be liters times molarity. And again, super important liters here when you're doing this part. So in a solution stoichiometry problem, a lot of times we will open up there the kind of the second step to get the moles by using the volume and the molarity, which will allow you to get to the moles of it. Also, the back end here is the second place where we will do a different thing as well. We oftentimes at the back end here will then have the moles, and perhaps we will have the molarity. And then you could get the volume, for example. You also could have the moles, and you could have the volume, like the liters or the milliliters, which will allow you to calculate the molarity. So those are two very sort of common endings to the stoichiometry problem, where maybe you're asked what is the concentration of an unknown solution, which is very common in titration type problems, or you may want the volume of something. So those are two sort of possible endings, along with our normal sort of ending moles to grams using the molar mass as well. So, there's a variety of ways that we could do this. So in those two steps along the way, somewhere usually molarity comes into play, and it could come into play in both of those steps. Everything else is pretty much the same. You still know that you have a limiting reagent problem if you have enough information to get to moles of each reactant. If you do not have enough information to get to the moles of each reactant, then it is just a basic stoichiometry problem. You don't have to worry about the limiting reagent part of it. Any questions on that there? So let's take a look at one here together, maybe. A lot going on in this question here. I regret it in a second here. Calculate the mass of solid sodium sulfate that must be added to 250 milliliters of a 0.25 molar solution of barium nitrate. So we're going to precipitate all the barium ions as barium sulfate. Also calculate the mass of barium sulfate that's happening. So clearly we got a stoichiometry problem happening here. So we need an equation. So we want sodium sulfate. So we want to make sure that we have the proper formulas. That's Na2SO4. And that's because sodium's +1, right? And sulfate's -2. Going to react with barium nitrate, which is BaNO3 2, and that is because nitrate's -1 and barium is +2. You should recognize this as a double displacement reaction, positive, negative guy, positive, negative guys. They're going to swap places, right, and partners. You should also remember, as we talked about, that when you do put it together on the other side, you want to get the right formula first. So sodium is really +1 and nitrate is -1, which means the proper formula here is NaNO3. It is not Na2NO32. That is incorrect. Barium is +2 and sulfate's -2. That will give us a BaSO4, and this is going to be our solid in this case. So that is our double displacement reaction. That is what we should form. And as we talked about previously, now that we do have the correct formulas down, the equation is not really good for us until we balance it, right? So we do need to balance it. And in this case, it looks like we just need perhaps a 2 there. And I think we should be balanced at that point. Any questions on that? So now that we have the equation, let's take a look at sort of what we're trying to find and what we're given. So we are given that we have 250 milliliters of barium nitrate. So we have 250 milliliters of this guy. It has a solution that has a 0.2 molar. And we want to know the mass of sodium sulfate. So that is this guy. So we want to know how many grams of this guy that we would need. We also, at the end, want to know the mass of barium sulfate formed. So we also want to know how many grams of this guy would you need it. So we have actually two separate problems in here that we could do with stoichiometry. First off, I do know that it is not a limiting reagent problem because frankly, the only thing that I could get moles of is this guy, right? I have no way getting moles of that guy, and I'm also looking for that guy. So clearly, this is just a basic stoichiometry problem. By the way, this is how I am going to get moles is by using both of those guys together, because if you have the molarity and you have the volume, you basically can get the moles by using really the molarity formula. Because we have molarity and we have volume, that's going to allow us to get to moles here. Moles again will be liters times molarity. And again, here we want to convert our volume into liters. We also perhaps want to use this as more of a dimensional analysis. So now that I have the equation, I'm going to get rid of that open space up there to kind of use it. And the first thing I'm going to do is take my volume and I'm going to convert it into liters. And that once again is 1,000 milliliters is 1 liter. That's going to give me 0.25 liters. Now that I have the liters, I'm going to multiply it by the molarity here. And once again, when I see something like 0.2 molar, that is the same thing as 0.2 moles per liter. So I'm going to use it as a kind of conversion factor so that I could clearly see where the units are. So 0.2 moles per liter, and this is our barium nitrate we are dealing with right now. That's going to allow our liters to cancel. And now we're going to do our 0.25 times 0.2. That's going to get us 0.05 moles of barium nitrate. First off, any questions on that? So using molarity and using the volume converted to liters allows us to get to moles. At this point, we basically have done step number 1. And this is basically step number 2 of our stoichiometry sort of procedure. Step number 3 is to do the mole-to-mole relationship. We really have 2 options in this case. We could either find our product or we could do our other reactants. We could do either one. So the first sort of third step I'm going to do is I'm going to do the mole-to-mole relationship this way to figure out how much of our other reactant that we need. So we could see from the equation that for every 1 mole of my sodium sulfate, I have 1 mole of my barium nitrate. So it's a nice 1-to-1 relationship here. So for the third step here to figure out our reactant, we'll take our 0.05 moles of barium nitrate. We'll use our mole-to-mole relationship from the equation, which is 1 mole of sodium sulfate is 1 mole of barium nitrate. The moles of barium nitrate cancel, gives me 0.05 moles of sodium sulfate. Yeah. Any questions on that? So that's just a stoichiometry problem to figure that out. We do want to know how many grams. So now that I have grams of it, I can use the molar mass from the periodic table to figure out now that I have the moles, I can use the molar mass from the periodic table to figure out how many grams. To do that, I will need the molar mass of this guy, right? So that is going to be 2 times 2299 for our sodium, plus a 3207 for our sulfur, plus 4 times 16 for our oxygen. So that's going to give me 2 times 2299 plus 3207 plus 4 times 16. That's 142.1 grams per mole. So we'll use that for our fourth step here, which is we want grams, so 142.1 grams per mole of our sodium sulfate. And that will get us there about 7.1 grams of sodium sulfate would be needed in this case. Any questions on the first part of the calculation? So really the same 4 steps. The only difference actually here was step number 2, molarity and volume to get to moles rather than, molar mass. Any questions up there? So in this question, we also wanted to know how much of the barium sulfate would we make. So we actually want to know as well how much of this guy. So we really could just pick up from the second step. We have the balanced equation. We converted what they gave us into moles, which means we could pick up right here and now do the mole-to-mole relationship going this way, right, between those two guys. So we could do the mole-to-mole relationship between those two. And we see it's kind of the same relationship, which is kind of nice. 1 mole of barium nitrate will give you 1 mole of barium sulfate in this case. So step number 3 for the second question, we're going to take our moles of barium nitrate. We're going to do our mole-to-mole relationship there that we got from the equation. 1 mole of barium sulfate gives us 1 mole of barium nitrate. The moles of barium nitrate cancel, gives us 0.05 moles of barium sulfate. We then need to do step number 4, which is how many grams. So once again, here we will need the molar mass of this guy. So that's going to be barium, which is like 137.3. Plus 3207 for our sulfur, plus 4 times 16 for our oxygen. That's going to give us a molar mass for barium sulfate of something with numbers. I'll go 233.4. So we'll use that here in a sort of last step, 233.4 grams per mole of barium sulfate. This is our second 4th step. And in this case here, 0.05 times 233.4, about 11.7 grams of barium sulfate would be produced. That also would be our theoretical yield, like normal, since it is a product. Any questions on that there? By the way, the nice thing about stoichiometry as well is you could have, if you didn't want to start from this guy, you could have started from this guy and did the mole-to-mole relationship and also figure out how much of your product you would make as well. You get the same answer. It doesn't really matter. Any questions on that? So again, the same sort of 4 steps, inserting molarity and volume and moles in either step 2 and step 4 or both. Yeah. Any questions? All right. So I did 1. Let's have you do 1 maybe. Is there 1 to do? There is. There you go. We want to know the mass of calcium carbonate that will form when you mix 25 milliliters of 0.1 molar calcium nitrate with 20 milliliters of 0.15 molar sodium carbonate. So take a few moments there, see what you come up with, and I'll give you some numbers that might help. calcium is 4008, carbon 12.01, and okay, so let's take a look, see how you're doing. So obviously here we need to start with the equation. We want to calculate the mass of calcium carbonate that's formed. So that's definitely a product. When we mix calcium nitrate, so that is going to be a reactant, with some sodium carbonate, which will also be a reactant. Once again, this should be a double displacement type situation. We're going to switch partners. Calcium, which is +2, carbonate, which is -2, which is why we get this formula here, which is CaCO3. That would be a solid in this case. Our sodium again is +1. Our nitrate is -1. So when they come together again properly, it is NaNO3. Again, not Na2NO3 2. That's going to be aqueous based on solubility rules. Once again, now that we have it proper formulas, we need to also balance it. And again, it looks like just a 2 there on the right-hand side will do the job. Any questions on that there? So again, just switching partners here, putting things together properly like we did with nomenclature, balance it to 0, and then balance the equation. Now we want to look and see what was given to us in this problem. We are definitely looking for the grams of this guy. We have 25 milliliters here of this one, and it is 0.1 molar. We also have 20 milliliters of this guy here, sodium carbonate, and 0.15 molar here. All right, so we balance the equation. Is this a limiting reagent problem? This actually is a limiting reagent problem because I have molarity and volume. I could get moles for this guy. And I have molarity and volume, which means I could get the moles of that guy. That means that this actually is a limiting reagent problem because of that. So again, we do pretty much do the same sort of steps, except obviously we do also have to take into account that limiting reagent aspect of it. Any questions on that there? So now that we sort of have an idea, it's a limiting reagent problem. It's still a stoichiometry problem. We really did part 1 here, which is get our equation and balance it. I'm going to use kind of the top part here again for a little bit more room. We are going to convert to moles, which is really the second step here. So we're going to do step number 2, which is basically convert to moles. So we're going to do the calcium nitrate first. Once again, we do need to convert our volume into liters. So if we take 25 and divide it by 1,000, we will get 0.025 liters. And that again is basically dividing this guy by 1,000, yeah, to convert it into liters. We will use our molarity again, not with the big M, but as 0.1 moles per liter, which again is what the big M stands for. And that is our calcium nitrate here. That is going to give us moles 0.025 times 0.1, 0.0025 moles of calcium nitrate. We're going to do the exact same thing for our other reactant. We're going to take this guy here, divide it by 1,000, which will give us 0.02 liters. We will also get rid of the big M and use the molarity properly here as a conversion factor of 0.15 moles per liter of sodium carbonate. Liters here will again cancel. And that will get us here 0.02 times 0.15. That's going to give us 0.003 moles of sodium carbonate. This is basically our starting amount, right, of each of those reactants. Any questions on that so far? So again, you do need to do a calculation as we talked about to figure out which one is the limiting reagent. So that is our additional part of this calculation, which is the limiting reagent part. I'm going to figure out how much sodium carbonate I need to use up all of the calcium nitrate. So I'm going to figure out how much sodium carbonate is needed. So to do that, I'll take the moles of my calcium nitrate, which is 0.0025 moles of calcium nitrate. I'll go to my balanced equation, and I see that for every 1 mole of calcium nitrate, I have 1 mole of sodium carbonate. That means that I would need 0.0025 moles of sodium carbonate is needed. Once again, I want to compare it to how much sodium carbonate that I started with. Do I have enough sodium carbonate? I do have enough in this case, right? So I have enough. I only need 0.0025. I have 0.003. That means that the sodium carbonate is the excess reagent. The calcium nitrate is the limiting reagent in this case. Any questions on that? The importance of that is, as we've talked about previously, it is always the limiting reagent that determines how much product we will make. So that means in this case, we want to use the limiting reagent here to actually figure out how much product we're going to make, which in this case is the calcium carbonate. So using that, we will take our limiting reagent to do step number 4, and we will take our starting amount of our limiting reagent. We will then go back to the equation and do the mole-to-mole relationship between the limiting reagent and, I guess this is actually step 3, and our product, which is 1 mole of calcium nitrate, 1 mole of calcium carbonate. So the relationship between these two guys is a 1-to-1 relationship. That's going to give me 0.0025 moles of calcium carbonate. My last step is then to convert it into grams, and I will need the molar mass to do that of calcium carbonate. So that's going to be 4008 plus 12.01 plus 3 times 16 from the periodic table, and that will get me looks like 100.1 grams per mole. So using that as a conversion factor here, 0.0025 moles of calcium carbonate. And we will do 100.1 grams per mole. Will tell us in this case here about 0.25 grams. That would also be, again, our theoretical yield in this case, as that is a product. So this is a good demonstration of you still have to, be conscious of when you're doing any type of stoichiometry problem, solution, regular, gas, it doesn't really matter. You still have to be aware that you could still have a limiting reagent situation. So you want to always kind of look out for that. Any questions on any of those steps there? So this is definitely one type of solution stoichiometry type problem where we do use molarity, at least in one place here in these type of calculations. Another type of solution stoichiometry situation that occurs is like what we're going to do in lab today, which is in titrations, for example, and neutralization type reactions. And in those type of sort of calculations, we sometimes will use molarity in both places. Kind of step number 2 and step number 4, we kind of use it in both places. So let's talk a little bit about that type of solution stoichiometry here. If I can find it, maybe. So in a neutralization reaction, we add, for example, strong acid is added to strong base, and they're completely neutralized. The net ionic reaction when we take a strong acid and a strong base together is basically the formation of water. So as we talked about, that is essentially one of the reasons why a reaction takes place. Remember that pretty much if you take an acid plus a base, you typically will make a salt and water. Salt, again, is an ionic compound. Obviously, water is water. Usually, water is made, especially in a strong acid, strong base situation, a lot of the H plus from the acid, the OH minus from the base is typically in a strong acid, strong base situation where the water basically comes from. Now, one of the common ways that we kind of do these type of reactions is through, as I mentioned a second ago, through titrations like we're going to do today. And when we do titrations, there's usually a situation that happens when you do a titration, which is you usually have what is sometimes referred to as a known solution. And a known solution means like the molarity of it, and you usually will know like the volume that you used of it. So you'll kind of know pretty much everything about one solution. Usually as well, when we do a titration, there's like an unknown solution. Okay. And with that unknown solution, maybe you only know the volume of it. You might not know the molarity of it or anything like that. So usually the process of titration is used when you have a known solution that you could use to react with an unknown solution. And what that allows you to do is a stoichiometry problem to figure out things about the unknown. You can figure out what the concentration is of the unknown, the molarity of the unknown type solution. We do a titration by a wonderfully drawn burette here. Looks just like that, sort of. You close your eyes. So we use a burette here. And burettes are also a little bit different, and we might have talked about it as we might have used it earlier, a version of it earlier. Burettes actually, the volume increases as you go down. So you fill the burette from the top, you empty the burette out the bottom. It has this guy right here, which is referred to as the stopcock. It's the on and off switch, basically. That's off, by the way. That is on parallel to the cylinder. You should always make sure it's off, obviously, when you're filling it. So when we fill a burette and we take a reading, it's really important to take a proper reading. So if our volume was right about there, this would be like 1.50 milliliters and not 2 point something. So it does increase as you go down. Whenever you use a burette, there's always two things that you should always take, which is you should always take an initial burette reading, so wherever the liquid is, and you should always take a final burette reading. And those two should always be done when you're doing a titration, for example, or using a burette, because you can find the volume added by taking your final volume minus your initial volume. So you can figure out how much you actually added by subtracting those two. Now, we usually will have something underneath. So let's just say, for example, here we fill this guy up with a base like sodium hydroxide. And we'll just say down here we have an acid like HCl. So in this case, we will add our sodium hydroxide to our acid. We also, when we do a titration, we oftentimes will add what is known as an indicator. And an indicator is something that will change color near what is referred to as the equivalence point. The equivalence point in a acid-base titration is the point where the moles of the acid will exactly equal the moles of the base. So you've added exactly, in this case, enough base to neutralize and react with how many moles of acid was there to begin with. That is typically where you want to stop your titration, which is sometimes referred to as the end point of the titration. The end point of the titration is where you stop, And if you do a good one, it should be really near the equivalence point. Indicators like everybody's favorite, which like we'll use today, which is phenolphthalein. Phenolphthalein is an acid-base indicator, and it changes color. And acid-base indicators always sort of work over a specific pH range. So for example, phenolphthalein works from a pH of 8.3 to a pH of like 10. And if you're not sure, below 7 on the pH scale is acidic, 7 is neutral, and above 7 is basic. So when we use something like phenolphthalein, if you put phenolphthalein into an acidic solution, it's going to be colorless, actually. And if you put phenolphthalein into a neutral solution, it will still be colorless. But when you put phenolphthalein into a basic solution, it turns pink. And that is why we use this indicator. For example, around 8.3, it's like colorless still. And as you kind of gradually go this way, it gets super pink. Yeah, fuchsia, super dark pink. You'll see it very shortly in an hour or so. It will get really, really pink. So when we do a titration like this, because the equivalence point, for example, in this type of titration is about 7-ish or so, yeah, you usually will want your indicator and your solution to turn the lightest shade of pink that will actually stay after you mix it. So light pink that you have to like take a white piece of paper and kind of put it next to it to see the pink. That's how light pink you actually would want your solution to be. And the reason for that is if you hit that really light pink, you're going to be in this area here, probably in your titration, which is probably near the equivalence point. If you get like super dark pink, you might be like way over here and you might be really past your equivalence point and stuff like that. So oftentimes we do use this acid-base indicator to change color near the equivalence point. So we have a visual representation of we should probably stop our titration at this point. You will also say this later on today, or some of you will say this later on today. And the very common thing that people oftentimes say when they're doing a titration is, I just added 1 drop and it went from like no color to like super pink. And you're like, what's the deal? How could that be? I just added 1 drop. It shouldn't have changed color that much. And the reason it does that is you'll learn in 1B, but a little preview of 1B. When you do a titration, you could plot what is sometimes referred to as like a titration curve, which looks something like this. And that's pH versus the amount of base that you add. So let's just say your equivalence point is right about there. We could see that as you approach the equivalence point, and this is typical of any type of like acid-base titration that you do, it goes pretty vertical as you approach the equivalence point. What that means is as I go from say there to there, does the pH change a lot? It changes a lot, right? Because it's going vertical. So that's pH over here. Now, does the volume actually change very much if I go straight down? Is there a real big difference in any of those points in terms of volume? There's not. And that's why when you add 1 drop and it goes from like colorless to super dark pink, it's not truly a big deal. You will come across instructors who will say, that's really bad. You should go do it again. And it's really not necessarily bad in all cases, because really, even if you missed it by a drop and you shot the pH over here, which is like 10-ish, and your thing is like super, super pink, you're not that far off from the same volume as really the equivalence point as to where you want. The reason why sometimes teachers will tell you that's terrible and you should do it again is because if you're not a careful titration person like me when I was in school, I would just open the thing up and like drain out, shut it and go pink, I'm done, right? So if you're not really careful, you could be like way over here with like the same kind of pHs over here. So you could be there and there, and this guy is going to be really super pink, right? It's going to be the same pink, right? And did I miss my equivalence point volume by a lot now? I did, right? So if you're really, really careful and you just like miss it by a drop or two, it's not really a big deal, the color, even though people put such an emphasis when people learn to titrate on, it has to be super light pink, super light pink. It's not really all that important. As long as you're really careful, you're going slow as you approach the equivalence point. But if you're not really careful, you could find yourself way far away from the equivalence point and have the same color. And that's why sometimes teachers will tell you to redo it and stuff like that. Any questions on that there? All right, so that's the saying that you should listen for later today. I only had one drop and went crazily pink. I don't understand. That's really why it happens. So when we do a titration, we slowly, for example, would add our sodium hydroxide here from our burette to our beaker. We would mix it. The pink color will come and then it will go. It will come and it will go. It will basically stay a little bit longer and longer as you're mixing before it goes away. That's how you know you're kind of approaching the equivalence point, and you might want to go slow as you get near that equivalence point in this case. One way that you could actually help yourself is if you see it's kind of staying longer and longer, you feel you're close to the equivalence point, you could let a drop form on the burette. You could take your wash bottle with some deionized water, and you could just wash that drop in and kind of dilute it and kind of dilute a drop in there. And that sometimes will help it not get so dark pink color. And that's called what is sometimes referred to as adding a half a drop as you do that by just kind of washing it in with your deionized water and stuff like that. Any questions on that? So this is a very common procedure where we use to figure out things like the molarity of an unknown. So for example, if I knew the molarity of my sodium hydroxide, and I clearly would know from adding it from my burette the volume of sodium hydroxide, I could then figure out the moles of my sodium hydroxide by using the molarity equation. I could also use stoichiometry to go from moles of sodium hydroxide to moles of HCl in my example from the balanced equation. I would then have the moles of the HCl. I would know at the beginning of my titration how many milliliters of HCl I use. I would then have the moles and the volume of the HCl, and that would allow me to use the molarity equation to figure out the actual molarity of the HCl if I didn't know it. And that's what you're going to be doing today in lab, which is doing titrations and stoichiometry to figure out the molarity, for example, of the HCl. Any questions on that there? All right, so let's do a problem here just to see how it all works together to finish it up. We got one here, maybe. All right, so for example here, what volume of 0.15 molar nitric acid is needed to neutralize 45 milliliters of 0.55 molar potassium hydroxide? So this is a titration problem, and when it says neutralize or something like that, it's really what we're doing here. For example, we would have set up our burette, and in our burette here, we would have 45 milliliters was used of a 0.5 molar solution of KOH, and down in like the beaker, we have the molarity here of 0.15 molar nitric acid. So we would need our equation. So we have our nitric acid and we have our potassium hydroxide. Remember that an acid-base reaction is also a double displacement reaction. So again, these guys are going to come together to make water. And our salt is our ionic compound, which is our potassium and nitrate coming together, which will give us KNO3. We want to also make sure that the equation is balanced. And in this particular case, it is balanced. I believe we should be good on everything. So we're good to go on that. The next thing we want to look at is what they gave us. We have nitric acid here. We have the molarity of it. And we are also looking for the volume that's needed. Here for the potassium hydroxide, we have 45 milliliters. And we want to figure out the volume here of, we have the volume. The volume is that, there you go. And the molarity is 0.55 molar. There you go. So in this case, this is a basic stoichiometry problem. We can get the moles of this guy. We obviously can't get the moles of this guy since we're looking for a volume. So we will start with converting to moles. So we're going to take our volume and convert it into liters by dividing by 1,000. So we'll take our 45 and divide it by 1,000. We will use the molarity of our potassium hydroxide, 0.55 moles per liter. And again, that is what the big M stands for, right? Moles per liter. The liters will cancel and we will end up with 0.045 times 0.55 gives us 0.02475 moles of potassium hydroxide. I'm not interested in potassium hydroxide. I do want to get over to nitric acid. So stoichiometry is next. It is a 1-to-1 relationship between those two in the balanced equation. So I could use that to get to nitric acid. 1 mole of potassium hydroxide gives me 1 mole of nitric acid. That's going to give me 0.02475 moles of nitric acid. So again, basically step 1, step 2, step 3. So in this case, though, when I think about molarity, which is moles per liter, I now have figured out the moles of my nitric acid. I was given the molarity of my nitric acid at the beginning. That means I could use the molarity equation here for step number 4 to figure out the volume. And for step number 4 here, our liters would equal our moles divided by our molarity if we rearrange it. So here we're going to use our molarity on the back end of the calculation as well. So I'm going to take my moles that I just calculated. I am also going to turn my molarity and use both units for the nitric acid. So I'm going to use 0.15 moles per liter of my nitric acid. And I'm not going to use it that way, but I'm going to use it the correct way, which is flipped around the other way. Which is why you want to use both units so you can see you screwed up like I just did there. So we actually want to put the moles on the bottom here so that they cancel. And liters up on top, which is what we're looking for. Moles here will now cancel. And we'll take divided by 0.15, going to give us 0.165 liters of nitric acid, which if we convert into milliliters would be 165 milliliters of nitric acid by multiplying by 1,000 in this case. Again, same sort of 4 steps in a titration problem. We just use molarity on both ends. Any questions on that there? Now, let's say to finish up, one little variety of question. We'll use this here since we have it. Let's say we had a slightly different question where we're not looking for necessarily the liters at the end, but let's just say, for example, here, we were told that we did this titration and it took 45 milliliters of 0.55 molar KOH to reach the equivalence point, right? To reach the equivalence point of a titration. And you started with, we'll go with 55 milliliters of nitric acid. Okay, so in this case, we're doing a titration. It took 45 milliliters to reach the equivalence point of this titration. We want to know what is the molarity of the nitric acid in this case. We would actually approach this the same way. We would take our base that we could get moles of. We would get the moles just like we did in the last one. We would also do the mole-to-mole relationship like we did in the last one to get us to nitric acid. Now, when we look at step number 4, and we are looking for the molarity, which is moles per liter, I have the moles of the nitric acid. I don't have the liters, right? But I can convert that into liters at this point. So I could convert that into liters, which would be 0.055 liters. And now I could actually figure out the molarity here, which is a very common titration type calculation. We'll take our moles divided by our volume that we started with in the titration. And that would give us, let's see how bad I did making up numbers here. A molarity of our nitric acid, in my example, would be 0.45 molars by dividing the two. So this is a very common sort of titration ending. You use stoichiometry to figure out the moles. You know the volume that you use, for example, of the acid. You now can take the moles like we just did here in this little calculation, divided by the volume of acid you started with. And now you can figure out what the molarity of your unknown acid is. Question on that variation there. All right, we will lay it up there for today.